Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about electron configurations. All right? And the idea of electron configurations is how do electrons arrange themselves around the atom? Okay? Because we know, because we've talked about this in previous videos. Let me bounce up here. I know there's a picture of it somewhere. Right here. Right? Electrons are like this yoga guy. Okay? They want to exist at the lowest, easiest place possible. So this position here is rather challenging to hold for a very long period of time, right? So when electrons gain energy, they jump up to like a higher energy level, but they're not stable, so they want to go to the lowest ground level. Okay, so in about 30 seconds, this guy will fall to the ground and he'll be back in his ground state. Okay, that's kind of how electrons operate. But what if there's an electron already filling in that ground state? Well, electrons have to go to the next lowest position, to the next lowest position, right? Because some of these atoms have lots of electrons, right? While others are rather simple, like hydrogen only has one electron, okay? It just fills the lowest subshell, okay? Or, etc. Okay, and if we go a little further, like carbon, we've got more electrons, but how do they fill? How do they arrange themselves? How do they get to the lowest energy level? Well, there's some rules that you need to follow. Okay. All right, so please make sure to write down this definition. Okay. And then we'll keep going. So pause the video if you need to. And I'm going to use this diagram as an example. If you want to draw this out, it may help you to visualize it, because sometimes drawing it out that's connected, there's studies that have shown that as you draw things out, they make sense to you. Okay. If I just explain it to you auditorily, it won't make sense, as well as if you wrote it out. So if you want to draw this out, you can, this table, and get some familiarity with how electrons fill. And here we have a couple different categories. We have the element, how many electrons it has. Okay, and we're considering all of these elements to be neutral. Okay, most of these elements actually in nature don't look like this, but if they're neutral, this is how many electrons they would have. And then we have an orbital diagram, which goes through and says this is how they're going to fill, how they're going to get to their lowest state. And then this is the electron configuration that we will assign to that atom, okay? And it's going to be the same because it's based on the number of electrons, okay? All right, so let's go through this. Remember how I told you last time in the orbital shell model explained diagram, okay? There's two things you need to be aware of. You have this first number that's in front of all of these numbers, all of these sections down here. We have 1, 2, 3, 4. These are energy shells. That's your pecking order. You start with the lowest energy shell and you work out. Once you're inside an energy shell, you have to follow the pecking order here, which goes from S to P to D to F. So they'll always fill from S, P, D, and F, right? We have our spheres, our dumbbells, and then out here we have our complex orbitals. All right, so this is how they're going to fill. So if we look here, all right, let's take, for example, hydrogen. We have one electron, so it's going to be right in this 1s box. And remember, each one of these boxes can hold 2 electrons. So helium will fill the next electron will fill in the same shell. And then we'll jump to a lithium. And lithium, this is full. It can't take any more. We got to go to the next place, which is going to be the next s orbital, which is in the second energy level, or energy shell, okay? And it's going to be the S shape. Now let's jump down a little bit, make it a little more complex. Let's go to nitrogen. Nitrogen has 7 electrons if it's neutral, so it's going to fill the first, the second, and then it's going to start to fill the p orbitals. Okay, now if you look here, they don't stack in the same box. They actually will spread out, and then they will start to backfill. So for example, if we had 10 electrons, it would fill the first, the second, and then we put 1 in each box, and then we come back and fill it again. Because you can imagine, these are both spheres. This is a small sphere, this is a bigger sphere, it's a bigger energy level, and then we have these dumbbell shapes, and you'll fill each of those dumbbell shapes with 1 each, and then you'll start to backfill and do it again. Now if you did sodium, this is full, we have an 11th electron, we can't put it anywhere down here, so we got to jump to the 3rd energy level. Okay, and where these electrons arrange themselves tells us a lot about its characteristics, about how reactive it is, or the way it reacts with other things. Okay, this is the basic idea of how they fill. Now, let's talk about why you can only put 2 electrons per box or per shell, orbital subshell. Okay, there's a thing called spin. All right, I'm going to say it as spin, but the idea is well, hold on. Let me. I'll have you write out this definition. So spin is a property of electrons that may be thought of as a clockwise spin or a counterwise spin down orientation, and a vertical indicates an electron and its spin orientation. So if you look here, all right, let's just jump down here. We have 4 electrons, okay, that we're trying to fill in, and we have one up and one down. So you can think of one of those electrons as spinning this way, and the other electron is spinning this way. But what happens if they're both spinning in the same direction? They'll actually repel each other, and they'll want to be away from each other. So the best orientation is for them to spin opposite of each other. That's why you can't have a third one in there, because they'll start to deflect each other and be off balance. And that's basically the idea of why there's only 2 per box, because they're spinning opposite of each other. All right. And as you start to fill, you want to start with the lowest energy level, which is 1. You put an up spin and a down spin. You put little arrows on the sides of them that kind of indicates which direction you're spinning. And then you fill in the next, and then you start to work through the other one. So for example, in oxygen, we have 8 electrons. And if you look at this, I bumped my camera. Stay with me. All right. We have 8 electrons. We're going to fill the first S, the second S, the next energy level. And within the second energy level, we have a p orbital, and we'll fill 1 per box, up, up, up. And then we'll go back and backfill the first one again. All right? And when we write the configuration for this, it's going to be 1s, 2s, and 2p. Those are the subshells that we're working with. And how many electrons are you going to be able to fit in each of these boxes? Well, the first one's full, so it's 1s2, 2s2, and then lastly we have 2p4. Okay? This number, the very last one, is the one that will always change, because guess what? What if you had 5? It would be 2p5. If you had 2 more, it'd be 2p6, because now you have 6 here. All right? And once it's full, we have to open up to the next level, which is 3s1. Because if you remember our diagram from before, okay, once we've filled this energy level with the pecking order that we're following, we have to jump to the next. And until that one's full. Then go to the next, and we work our way. So it's kind of like you start here, and you work left to right, left to right, left to right. Okay? All right. Now, let's do this one. We've talked about this picture, about stability. I want you to fill in this electron configuration for iron. Okay, iron is element 20. Oh, you can't see it. It's right in the middle. It's 26. So we're going to have 26 electrons. How are we going to fill this box? Okay, so I want you to pause the video. I want you to try your best. And then I'm going to come back through, and I'm going to do it with you. Okay? So let's pause the video right now, try it, and then I'm going to do it with you. All right, so you should have done it. Okay, you shouldn't have cheated and kept watching this. All right, so I'm going to fill this in. All right, all the way to 26. I'm just going to write it above it so I don't write it in my book. So we've got the 1s. We have 1, 2. We filled that box. We fill the second one. 1, 2. So now we're at 4. And then we're going to go 1, 2, 3, up, 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 and then down, down, down. So now I'm at 2, 4, 6, 8, 10. I'm going to put a line here. This is 10 electrons. And we have to do 26. We got to keep going. Okay? So now we have the next energy level, which is 1, 2, 3, 4, 5, 6, 7, 8. So I'm filling in this next box. So now I've got another 2, 4, 6, 8. All right, let's go, keep going until we get to 10 here. So we'll go another, fill in this 4s, right? Because this first number refers to the energy shell. And then inside that, we have a pecking order of s to p. So we have another 2, 4, 6, 8, 10 right here, 10 electrons. So now we're at 20. So now we have 6 more left. Now, this is where the rules get a little fudgy or confusing, because now we're putting 3D before 3P. But there are some rules that get a little bit broken, okay, as you get to more complexity. I will not expect you to solve problems of this complexity on your test, but for the sake of this example that's written here, I want to use the 3D block because it's actually a lower energy than the 4P. All right, and it gets a little complex. If you want to learn about it, we talk about it in higher classes and in AP. All right, so then we're going to fill this next block. We'll do 1, 2, 3, 4, 5, and we got to come back and fill in right there at 6. So that's how we would fill this. And the rules start to bend a little bit as you work your way into higher levels, and it's okay. We're not going to get into it in regular class. This example goes a little bit further than I want to go. Okay, but keep in mind, as we fill our energy levels, we have to follow the order at which these of the lowest energy. Okay, there's 2 pecking orders: the energy level and then the suborbital. So we have S and 1s, and then this one is 2s and 2p, and then we have other complexity. Okay, now let's look at an example of patterns that we see in the periodic table. All right, we have the S, the F, the D, and the P blocks. So as you work your way across, you'll actually find that you'll work your way this way, and you'll come back, and you'll keep working your way around as you work your way down. So 1S, there's no other S over here. There's no 1P block. Okay, in the second energy level, actually, let me back up. When we talk about energy levels, like 1, 2, 3, 4, as we work our way out further from that last diagram, those are correlated with the periods of the periodic table. They actually work their way down like this. So you can imagine there's 7 energy levels. Okay, in the images we were showing you, there's only 4, but there's more than that. And as you work your way across the table, you'll actually start to run into more complexity as you work your way down. Because as you work your way further out, you can fit more and more electrons, and they configure themselves in different ways. So if you think of elements like hydrogen, okay, there's a missing one right here. That's actually on this side. That's part of the S block. The second electron will actually be an S. But because of how their characteristics are, helium is more like neon, argon, and krypton. And we'll talk more about that. While hydrogen acts more like lithium and sodium. So that's why helium actually got bumped over here. And then we have the S block here, and then we have the P. You see how in the S block we only can hold 2 electrons, right? Beryllium has these 4 electrons. There'll be 2 in the first S level, and then the second one will be up and a down spin here. So you actually can track where electrons are just by where it's at on the table. And you notice the P block has 6 spots available because these ones here, their last electron is located somewhere in this 2p block. So if you want to tell you where the last electron is of sulfur, you find, well, it's in the 3rd period, period 3, and it's in the p block. Okay, so we have the S, the P, the D, and the F. We will rarely get into the D and F blocks as far as electron configurations go. Okay, as far as solving problems and working with them, we'll also be working with elements at the top of this table. All right, so you can tell me, because the idea when we're thinking about atoms and their characteristics is where is the very last electron found? Because that's the one that's going to be interacting with the world. The other ones that are inside are kind of hidden away. But the ones on the very outside are the ones that interact. So it's good to know where they're located. Okay, so for chlorine, we would have, this is in the 3p block, so the very last electron is probably going to be 5n. Okay, now, you can pause the video and just appreciate this image, because they're going to do osmium. It's a little more complex than I want it to go, but it will give you an appreciation for how we order, just like we did iron a moment ago. Okay, now let's talk about noble gas configurations. This, I want to write down this definition for valence electrons, because valence electrons are in the outermost shell. So when we're thinking about electrons, you got to think of them as the farthest ones away. And when we think about them, we want to start with what period they're in. So period 1, energy shell, or I'd say energy shell 1, 2, 3, 4, and as you work your way down to 7. All right. If your number of your elements stops here, then these electrons are going to be in your outer shell, that energy level. So there'll be 2 in the S that are on the outside, and then you'll have some that are in the P block that are also on the outside. All right. And when we're writing them, we can actually use checkpoints to describe them, because if you look down here, there's a great image of this. Okay. We have an inner core electrons and we have valence electrons. So this inner core electrons, we've got the 1s is full, the 2s and 2p are filled after that, and then we don't need to write these because they're all full. So we actually can use a checkpoint, which is one of these noble gases which are found at the end, because you'll notice the pattern repeats. Once you hit the end, it repeats. So everything above a certain checkpoint is basically already filled. The ones we really care about are the ones that are not filled in that energy level. So the ones that we stop at, for example, in sulfur, we stop in the 3 energy level, so we'd use a checkpoint up here. So the checkpoint, it would be neon. All right, we have a checkpoint. So we can say neon, and then we can write out the configuration, like this down below. If you look at this image, it puts it together pretty nicely, because this is full. You can just write neon in brackets and then write out that last layer. It just takes some practice. Come talk to me if you're a little confused. But the idea is the noble gases act as a checkpoint. All right? And there's one last way, and this is the last thing I'll talk about, that we can write out and describe atoms and their electrons. We have valence electrons in form of electron dot structures. Okay? So we have an element, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And we can write their noble gas configurations with neon, because that's our last checkpoint. And then you can write out their configurations. You can see that as you work your way across the table, they get more and more electrons, and they fill in a certain pecking order. And you notice that each one of these, as they gain electrons, they'll fill the S and then the P, and then the number of valence electrons increases, right? And we can draw them down below as sodium, magnesium, aluminum. We can draw dots around them. So you can draw a dot here, and then we have magnesium, we have 2, and then aluminum, you put 3, and then silicon, you put 4. And then you can start to double up all the way until you get to argon, which is 8. And you'll find that when you're using S and P blocks to draw out these electron configurations, you'll always hit 8. Okay? So I want you to take a moment. You can draw this image out. I would like you to, and to appreciate it, to understand that as you increase the number of electrons that are available, they will fill the S and then the P subshells, and then the number of electrons will increase. And how we organize them in an electron dot structure is by putting a dot around them. So it's signifying how many valence electrons there are. All right? This is a very useful model when we start to draw bonds. Okay? So please take the time to draw out this image. I appreciate it. Thanks again for watching. Until next time.